So this week we have the pleasure of having Richard Hind from Notre Dame, who's going to speak about isotopies and squeezing of Monotone Lagrangian Tori.
And thank you for the invitation. Right, yes. So I suppose the goal here is to, eventually is to get some sort of quantitative estimates on squeezing monotone Lagrangian tori. So how small a ball can you move them into, and also how much space you need for isotopies, or whether isotopies have to go through some divisor. So I think this is interesting even for non-monotone Lagrangians, but we have a big list of monotone Lagrangians which seem to be amenable to computations. So we'll try and do that. Okay, all right, and this is joint work with Grigory, Mikhalkin, and Felix Schlenk. All right, so let's do this. Right, okay, well, so I'll put, there's one general result. So X is four-dimensional. It's going to be a monotone symplectic four-manifold. So that means either CP2, S2 times S2, or blow-ups. Right, just monotone. So, right, so the monotone symplectic form, and I'm always going to normalize that so the symplectic form is equal to the Chern class. Right, so we're going to so normalize, so it's monotone. Normalize. Just to fix this once and for all. So if you take the Chern class, is any compatible almost complex structure, this is equal to the symplectic form as a cohomology class. So in particular, if it's CP2, then lines have area 3. Right, and then okay, L. So this is a monotone. This is a Lagrangian torus, monotone as well. So monotone Lagrangian torus. And with these normalizations, this means you get the same formula but in relative cohomology. And so it's the same thing. So C1 is omega. Also as a relative class. Well, so another way to say this, so this it's the same thing as saying that so Maslov 2 disks have area 1. That's how we're normalizing it. So Maslov 2. Yes. Area 1. Right. So we like to do this. It just makes it convenient. Right, then a homology class. So A is a homology class here. So I want to assume, and then there's some assumptions. So I want to assume the Chern class is either 1, 2, or 3. Right, and it's represented by a symplectic sphere. Represent an embedded symplectic sphere. Okay, I think that's it. All right, so then, right, so there's exactly, so C1 of A is a number, so there's exactly C1 of A Hamiltonian isotopy classes of, all right, so symplectic spheres, X minus L. Right, so symplectic spheres in the complement of L representing this class. So they're all in the same homology class in the monotone manifolds, but there's exactly 3 Hamiltonian isotopy classes in the complement of the torus. So in particular, you can push. So the thing is, so you can take your symplectic sphere, you can push it off by Hamiltonian isotopy, you can push it off the torus, and you can do that in exactly 3 ways. So, all right. So
the Hamiltonian isotopy are supported away from L.
Yes. Right, yes, exactly. Right. Yeah, exactly. Right. So the equivalence relation is two spheres in the complement of the same if one could be mapped to another by a Hamiltonian, right, supported away from L. Exactly. Yeah. Right. Okay. Right. Yeah, you're right. Of course, they're all Hamiltonian isotopic in the ambient space. Oh, well, I mean, they might be. Okay. Right. So it's right. So I'll give you a very rough outline of this. Just see why this is true. Sorry. Then once we have this, then everything else is really computations in these particular examples. Right. Okay. So why is this? Well, this is the next stretching argument. Right. So it's well. So it's right. So we'll do the case. Right. So for example, so main example maybe if I take X to be CP2, then the only option for the Chern class is 3, and then I'm looking at the class of lines. Right. So A is going to be the class of a line. And then same thing, right? So now I have a monotone Lagrangian torus in CP2. And then I'm claiming there's exactly three Hamiltonian isotopy classes of symplectic spheres in the complement of the torus, no matter which torus you choose. Right. Okay. So we know, right. So in this case, actually, we know there's only one Hamiltonian isotopy class of spheres in CP2. They're all Hamiltonian isotopic. Okay, all right, so how to do it? All right, so it's right, so basically so following Gromov. Right, all this. Right, so following Gromov, you choose an almost complex structure. And so whatever choice you make of almost complex structure, you can choose 2 points. CP2. Then there exists a unique holomorphic sphere through the 2 points. Then there exists a unique J holomorphic sphere whose image intersects x1 and x2. Right, this is true for all x1, x2. So I can fix x1, x2 on the Lagrangian. Right? So I want to fix x1, x2 on the Lagrangian, maybe generically. Right, take a tubular neighborhood. All right, so neighborhoods. By Weinstein's theorem, a neighborhood of the Lagrangian sort of looks like a tubular neighborhood of the zero section in the cotangent bundle. So we can think of this as being some sort of epsilon disk bundle in the cotangent bundle of a torus. So this is U. Okay, and then I want to stretch. So start changing J, and I want to stretch J or degenerate J along the boundary of the tubular neighborhood. Okay. Well, of course, a lot of stuff going on here, but anyway. So turns out there's 2 things can happen, right? So there's two possibilities. So you start stretching J and then taking a limit. 2 things can happen. Yeah. Right. So, right, if you take limits of holomorphic curves when you degenerate the almost complex structure, they converge to holomorphic buildings. They can have components in maybe you get a component in the cotangent bundle of L or the tubular neighborhood of the Lagrangian, and also in the rest of the manifold. Okay, so in here we've got the Lagrangian, and then we've got 2 points, x1, x2 here. So one option is that you get a pair of pants inside the cotangent bundle, and then three planes, compactified with 3 disks outside of the Lagrangian. By the way, this results, we're using monotone. I think this is false. There could be a lot more isotopic classes if the thing's not monotone. But since this is monotone, all these planes have to have integral area. My initial plane only has area 3, so the areas have to be 1, 1, 1. In other words, you can't get any more complicated degenerations here. So using monotone to simplify this. That's one option. So what's going on? These are finite energy planes. They're asymptotic to in principle, a Reeb orbit on the boundary of a cotangent bundle, but we just think of those as oriented geodesics. So these are planes asymptotic to geodesics on L. It's one option, or possibly you get two cylinders inside. So one would go through X1, and one goes through X2. And then, right, I'm only allowed three components outside, so you have to get a cylinder and two planes. Right. So that's it. Turns out with the monotone conditions, those are the possible degeneracies. And then, right, and then the plan is to take these holomorphic buildings and kind of push them off the Lagrangian in exactly three ways to get three spheres in the complement. All right, so two cases here then. Okay, right, so I suppose, right, so case one. Right, so my goal is to take this kind of arrangement of finite energy curves and kind of somehow deform them and build a closed sphere out of it. Okay. All right, so the trick is to look at what's happening near L. So near L, so well, not right on U. So there's a projection map. I can take U, which is a subset of the cotangent bundle, just map it to R2, just onto the momentum on the P1, P2 orbit. Right, so just take the moment map. U. Right. Okay. So if you did that, the Lagrangian would just go to the origin. Right. So these things are asymptotic to geodesics. To cylinders over Reeb orbits. So that means if you project them down on this map, the cylinders over Reeb orbits are going to project down to just line segments. So it's a line segment in the P1, P2, and then you've got to multiply by a circle in the fiber, right? So I'm quotienting out, right? So that the fibers here are T2s. So the cylinders project down to a line segment in P1, P2, and then you multiply by a circle in the fiber. So this is going to represent a cylinder. Our three planes there are asymptotic to cylinders, so I'm going to have I'm going to have three cylinders coming down. Not exactly. And then if you look at the projection as you approach the Lagrangian, the planes are asymptotic to the cylinders, so the projections would look something like this in a neighborhood. That's very rough. In other words, if you got close enough to the Lagrangian, they'd look exactly like line segments in the P coordinates multiplied by a circle in the Qs. And the circles would be in the homology class of the geodesic that they're asymptotic to. So that's the picture. All right. Okay. Right. Okay. And then these three directions add up to zero. It's exactly because the three boundary circles were bounding a pair of pants in the cotangent bundle. All right. So I want to perturb this. So you can perturb the cylinders just by by shifting it in the P direction. So I could do maybe on the one. So this is the projection of the first disk, second one, third one. I could just move the cylinder just by pushing it in the P coordinates and leaving the Qs the same. So this is a new line segment multiplied by S1. So this is a new cylinder. I could push D1 a little bit like that. I could push D2 a little bit like that. The D3 cylinder a little bit like that. This is three cylinders. I know I can fill them in with a pair of pants, so I can join these up in some sort of, right? So this is a symplectic pair of pants there. I know that's possible exactly because I can look at the building and see it's possible. So I can fill that in with a pair of pants. This gives me, I suppose, a bigger pair of pants. But now, because of index conditions, intersection conditions, I can extend this perturbation here to push D off itself completely. So we can extend it like this. Right, so in other words, right, so just by translating in the P's, I can push the cylinder part of D1 off itself, and then I can extend that to a deformation of the whole of D1, which is completely disjoint from D1. So that's because these are Maslov 2 disks means you can push them off themselves by this kind of perturbation. So, okay, so this is now a symplectic sphere in the complement of L. Right? And so this is a symplectic sphere, but we notice that it intersects, in this case, D3, but not D1 or D2. So it's right, so it's a sphere in the complement of L. I could do the same kind of construction and produce one that intersects D2 and not the other two, or that intersects D1 and not the other two. So there's three ways to do that, and actually you're going to get different homology classes because the intersections with these relative classes are different. So the upshot of this is that you get three spheres. So that's halfway there. So I proved that there's at least three if you get this kind of degeneration. Proved. Okay, so that's case one. Actually, we can use, turns out, if this happens, all right, so now we can use a result of Dimitrov. Result. Goodman. So they have various classification results of Lagrangian tori and cotangent bundles. It turns out, right? So it turns out if you have this arrangement, we can actually see that L is it's homologically non-trivial. So the homology class of L is not equal to 0 in, right? So now it's right in the homology of CP2 minus those three spheres. That's one, that's two, that's three. So if you remove the three spheres, right, I've got the three spheres disjoint from L, you take those out, L actually represents a non-trivial homology class in the complement. And by this, and the complement of these three spheres looks like, well, just like a subset of the cotangent bundle of the torus. This is homologically non-trivial. And then by Dimitrov, Rizal, Goodman, Ivry, this implies that L is actually Hamiltonian isotopic to the Clifford torus. I'll tell you what that is in a second. So we'll do an example of that. But it's the easiest torus you can write down. So in fact, I know exactly, if this arrangement happens, we know exactly what L has to be. It's kind of it's a special sort of, just basically a product torus in that case. So, right, so in other words, that's case one. So that's right, so in a sense, we're more interested in case two. So case one only deals with one particular kind of Lagrangian torus, which I know a lot about already. So maybe we're more interested in case two, but the argument's sort of the same, right? So case two, well, except, all right, so what's going on here? So these are all asymptotic to geodesics on the Lagrangian. It turns out for cylinders, if this is asymptotic to a geodesic gamma, these cylinders go between a geodesic and the same geodesic with the opposite orientation. So you can obviously imagine them just looking like derivatives of geodesics. And so just cylinders over a geodesic. The two ends are going to be the geodesic with opposite orientations. Same for this one. But since these two cylinders have to be disjoint, this has to be gamma prime minus gamma prime. And gamma prime are in the same family of geodesics. So that's what's going on in case two, which unfortunately means when you project them down onto R2, those two, all of the asymptotic ends are kind of in the same direction. So it's hard to draw. So everything out here is disjoint. These are three disjoint holomorphic curves. I'm taking limits of embedded curves. But when you project them down, they're all going to project down sort of on the same line segment. So the fibers will be different circles in the same homology class. But they're projecting down more or less onto the same line segments, but the two disks might kind of veer away. So you get one disk sort of projecting down like that, maybe another one like that. And then here you get, so in the rest of the manifold, there'd be some kind of cylinder right there. Okay, and then again, there's three ways to do it. So now we have two cylindrical branches cutting across the Lagrangian. I want to perturb in two ways, in three ways. So you can either put one branch to one side, put two branches to one side, or two branches to the other side. So that's three, at least three ways to do it. So again, you get three spheres. There's two cylinders going through. I can push one to the left, one to the right, both of them to the left, or both of them to the right. That's it. And again, that's three different homology classes. All right, so again, you can intersect with relative classes and show these are different. There's something to show conceivably there's four. Because since you have two branches going through, you could push the first one to the left and the second one to the right, or the second to the left and the first to the right. But it turns out that's the same. They turn out to be the same. So there's three classes. So that's there, right? So there we go. Right. So what this shows is there's always three spheres in the complement of the Lagrangian. We want to show there's exactly three. In other words, I want to say if I just take a random, all right, so step two. Right, so I want to show that any symplectic sphere in the complement of the Lagrangian is Hamiltonian isotopic. Right, so again, with compact support in here, Hamiltonian isotopic in here, to one of the three that we have. Or these are in different homology classes, so you can't be isotopic to more than one. Right, so this is a degeneration argument. So you take your sphere, you sort of start deforming the almost complex structure and sort of force it to degenerate. So I can take my sphere, it's going to degenerate to a holomorphic building. It has to be of one of those types. And in fact, once you get one degeneration, everything has to be of this kind. It can't, if I found one sphere degenerating onto a building like this, I can't, then every degeneration has to be onto the same thing. In particular, if I degenerate this random S, it's not going to be asymptotic to different sets of geodesics. Otherwise, you get by an intersection count. If it was asymptotic to some gamma 2, it would be intersecting this building twice, and somehow that's not allowed. So I'm in the class of a line. So, right, so you show it has to degenerate onto a building of the same type, and then you can show sort of just before the degeneration, it has to be one of these three that we've pushed off. So anyway, so it's I'm going to claim that's the proof of that. So it's very, very sort of geometric. We can almost see what's going on here. You believe that or not? So it's, right. So that's right. So it's okay. Right. So this is a general. So I'm claiming this is a general result. Well, if you don't like it, we can do some examples. So I suppose, so we can test this on some well-known tori. Sort of easy to see. All right, so, well, there's this Clifford torus I was talking about, right? So the Clifford torus. So we can draw this just a regular moment polytope. I'm just doing the CP2 case. So we can do the regular moment polytope for CP2. It's just a right angle triangle here. But because of my normalization, the sides have length 3. So it's supposed to be CP2. Although this is the moment polytope for CP2. Right, so it's that's a CP2 picture. The Clifford torus is just the monotone fiber over 1, 1. So the fiber over here is a Lagrangian torus. Then you can see, I'll come back to this, but we can somehow see two families of holomorphic disks here. Both have area 1. This is monotone. I'm claiming there's 3 spheres in the complement, but we can just see just the 3 axes of CP2 give the 3 spheres. All right, so it's right. So we have I'm going to call them SX, SY, S infinity in CP2 minus the Clifford torus. This SX. So at least, okay. This doesn't prove there's exactly 3, but I suppose it shows, at least in this case, there's at least 3. Those are the 3 classes. Maybe another one is the next one people look at is the Chekhanov torus. Right, so it's a bit right. So to do this, we have to fix. I have to fix a circle in the complex plane. I think it has to bound area 1/2 gamma here. So it's area 1/2. And the important point is it's disjoint from itself if you reflect in the origin. So we fix this gamma, and then the Chekhanov torus is right. So I'm going to give you a set of points in C2. Right, so what do I want to do here? Right, so it's a set of Z e to the I theta, Z e minus I theta, where like theta anything, and Z is in gamma. So this is the Chekhanov torus. So we take this circle, put it in the diagonal, and then rotate it around by the theta action here. So theta circles bound area 0, and the gamma circle, when you map it into the torus, that bounds area 1. Turns out to Maslov class 2. Okay, well, so this is, we look at this, so, well, the absolute value of Z1 is equal to the absolute value of Z2. So if you include this in the moment image, right, if we include this in the moment image, it's going to be kind of sitting above, the diagonal. Also, gamma is more or less sitting in a disk of area 1 plus epsilon. Because I need a half on both sides. So it's almost sitting in a cube of side length 1. Anyway, so this is the projection. Under the moment projection, this is the image of the Chekhanov torus. Anyway, so the same thing is true, right? So Sx, Sy, Sc, they're all in the complement. And again, they're in different homology classes by some linking arguments. So again, right, so we get Sx, Sy. So again, right, they're also in the complement of Chekhanov torus. Right, so there's 2 examples. So what we're up to so we want to relate tori and CP2 to tori in the ball. So next, there's a map where you input. So I input pairs. L is like again, right, a monotone Lagrangian torus and CP2. S is right, so usual vector symplectic sphere in the class of a line in CP2 minus L. So if I get a pair, if I choose right, I fix the monotone. So remember this is monotone Lagrangian torus. Right, so I'm given the pair Lagrangian, and I pick one of the spheres in the complement. You can map that to Hamiltonian isotopy classes of monotone Lagrangian tori in the ball. So just to fix notation here, B43. We can make this a definition. This is a ball of capacity 3. I can just define that to be CP2 minus the line at infinity. Okay, right, so this is a ball of capacity 3. All right, so the map is, right, so it's just LS maps to, I suppose the Hamiltonian isotopy class of phi of L, where phi is a symplectomorphism of CP2 with the property that phi of S is S infinity. So such a symplectomorphism exists by graph. There's only one Hamiltonian isotopy class of symplectic spheres in CP2. So I can find a symplectomorphism of CP2 which takes our sphere to infinity, but our sphere is in the complement of L. So if this sphere goes to infinity, the image of L is going to have to be disjoint from infinity, which means it's in the ball. So again, so that's a map, and right, and this is well defined, right? So this is well defined. In other words, we check. This is independent of the choice of phi. Phi. But maybe it does depend on S, right? But it's going to depend only on. Well, it depends. Let's start on the Hamiltonian isotopy class. Of S. So, okay. So it says all I'm doing, I'm just taking a sphere in the complement, moving it to infinity, and then the Lagrangian is going to end up in the ball. But there's three choices of S. So particularly, so in principle, you get three Hamiltonian isotopy classes in the ball. So what we get here. So I suppose. Write it out. Right, so Hamiltonian isotopy class in CP2 gives you, by this principle, well, right, so I have to choose S in the complement. There's three possible choices of S. They could give you three classes over here, but, well, maybe some of them are the same. But what we can say is we're going to get at most, I suppose at most, three classes, three Hamiltonian isotopy classes. In the ball. So, it's at least, so in principle, at least, there's 3 times as many isotopy classes in the ball as in CP2. And in fact, but the thing is, if you're in there, if you started with the Clifford torus, right, then we have the 3 isotopy classes of spheres. So of course, so here there exists a symplectomorphism which preserves the Clifford torus, but maps Sx to Sy just by switching the 2 factors. Or right, so, either one. Or you can also, well, you can map the factors around as much as you want. So I could map Sx to Sy or Sx to S infinity, fixing the Clifford torus. Which means you're only going to get one Hamiltonian. So that means, right, so all of these things, Sy, S infinity, they're going to give the same, isotopy class in both. Because if I want to move Sx to infinity, I could move it first of all to Sy. Nothing happens to the Lagrangian torus. I guess then move Sy to infinity, still nothing's going to happen. So you're always going to get the same isotopy class in the ball. It's just that's just the Clifford torus. Okay. So I get 1 in this case. In the Chekhanov case, the same applies, right? So if I switch the 2 factors, you map the Chekhanov torus to itself, but again, you map the x-axis to the y-axis. So the x-axis and the y-axis are going to give you the same Hamiltonian isotopy class in the ball. So it turns out in this case, and there's something left to check, but in this case, you get 2 classes. There's some symmetry. The x-axis and the y-axis give you the same one. So, all right. Okay, so those are the cases we can kind of write down very explicitly. All right. Okay, so now, but these aren't the only examples, as it turns out. So there are a lot now, in fact, infinitely many. So in fact, now we know that there's infinitely many Hamiltonian isotopy classes of Lagrangian tori in CP2. Go with this. So in fact, right. So we know now there's infinitely many Hamiltonian isotopy classes. Lagrangian Tori. Right, I'll write down some theorems in a bit, but so in one way or another, I think they all come from weighted projective spaces, right? So they come, right, so they come from weighted projective spaces. So you can look these up. Weighted projective spaces. All right, so I choose, I need three numbers, RST, natural numbers, pairwise co-prime. Right, okay, and then we can define the weighted projective space, so CP2 RST. I want to think of this as being symplectic, so I'm going to see this as being a symplectic reduction, right? So when we think of one definition, this is a symplectic reduction of the boundary of an ellipsoid. Boundary, right? And the ellipsoid is right. So R, I'll stick pi in here. Z1 squared, S, Z2 squared, T, 3 squared. Put it boundary here equals 1. So this is a subset of C3. Right? This is a hyper smooth. This is a smooth hypersurface in C3, right? The simplex. So you're going to restrict the symplectic form to this. It's going to have a one-dimensional kernel. You quotient out by that kernel, and that gives you the weighted projective space, right? And it inherits a symplectic form from C3. So what about this? So it's well, this thing's invariant under T3, right? Because it can rotate in the three factors. But I'm quotienting out by the kernel of the symplectic form, which is generating an S1. So what's going to be left? Well, it's still going to be toric. There's still a T2 action. So this is still going to be toric, symplectic, but it's not a manifold, right? Because if you look at the, so we're quotienting out by the characteristic direction, which goes in kind of like the, right, sort of the RST direction. If you look on the Z1 axis, that's going to be a short orbit unless R equals 1. So there could be, so in general, this is going to be an orbifold. Actually, 3 orbifold points. So you get an orbifold point on the quotient of the Z1 axis unless this coordinate R is 1. So it's going to be an orbifold point on the quotient Z2 equals Z3 equals 0, unless one of the coordinates is 1. So that's right. So these are the weighted projective spaces. So we can think of them as toric, symplectic, orbifold stuff. Right. And then the moment image is basically just draw this plane in R3. Right. Okay. So right, we've got those things. Right. But then no. So right. So the key, the big discovery here. Right. Okay. So there's an assumption. So if ABC is a Markov triple. Right, so these are 3 numbers. So that means A squared plus B squared plus C squared is 3ABC. So these are, so there's a lot of solutions to this equation. If you find a solution to that equation, then so then we can take the weighted projective space. I've got A squared, B squared, C squared. This is an algebraic degeneration of the plane of CP2. Right, so this, talk about what that means. All right, so this is an algebraic degeneration of CP2. Except, so these algebraics, so in other words, you can sort of, you can get some complex three-dimensional thing with a singular three-dimensional variety fibered over the disk. The smooth fibers are copies of CP2, and the singular fiber is this weighted projective space. Plus, we can think of all this whole thing as sitting in some ambient symplectic manifold, so that the symplectic form, so we can induce symplectic forms on the singular fibers. But right, I've already got a symplectic form on this, but I want to scale it, just to make sure that when I go to the singular fibers, that the lines still have area 3. So there's some scaling factor here. Okay, so these weighted projective spaces are algebraic degenerations of CP2, or there's also work Vienna on this, thought of it sort of a completely analogous story. If you take the moment polytope, you can, well, if you know about almost toric vibrations, if you take the moment polytope, you can decorate it with nodes and branch points, and then you get an almost toric vibration for CP2. So it's okay. Right, so all the moments. So these things have a moment polytope, toric, or the moment polytope is the base of an almost toric vibration of CP2. So these things sort of amount to the same thing. So there's 3 orbifold points. What it amounts to is kind of taking out the point and sort of surgerying in a smooth symplectic manifold with that. Okay, right. So and then once you know this, there's at least away from those orbifold points, there's a symplectic parallel translation from the singular fiber to the smooth fiber. These singular fibers have moment polytopes. They're going to have a monotone fiber. You can push that monotone fiber to the smooth fibers by parallel translation. That gives you a monotone torus in CP2. So the upshot here is that we get a monotone Lagrangian torus ABC in CP2. Right. So that's sort of the discovery here. Well, I was trying to write down something explicit, but we can actually write. Right. We'll do this. Right. So actually, we'd see to draw some of these, right? So, for example, as far as those Markov triples go, so if one of the numbers is 1, then the other 2 have to be Fibonacci numbers, it turns out. Whichever way we're doing it, right? So the other 2 where. So Gn, these are the odd index Fibonacci numbers. So Fibonacci numbers, if you go something like, what's it, 1, 1, 2, 3, 2, like 1. The odd index one, so I'm going to go 1, 2, 5, 4. So I can get 1, 1, 2, 1, 2, 5, 1, 5, 3. So these are exactly the Markov triples where one number is 1. 1, 1, 1, I guess, as well, but we know about that. So 1, 1, 1 is just the Clifford torus. So these are exactly the Markov triples which are going to have a smooth corner to the polytope, right? Because the orbifolds, you have an orbifold points only if the parameter is not 1. On the other hand, if the parameter is 1, then you're going to get one of these examples. And then when I draw the moment polytope, because it has a smooth corner, the moment polytope is going to have a right angle. At least I can assume that the moment polytope has a nice right angled corner. So it turns out, if we put that at the origin, so this is now the moment polytope for the weighted projective space. I can arrange it to have a right angled corner at the origin. And then it's just a question what the side lengths are. So it's so these are related to the squares of the 2 numbers. It turns out right with my rescaling system, this turns out to be Gn divided by Gn plus 1. And this one is 3gn plus 1. So that's the moment polytope for these particular Markov triples. 1,1 sits inside here, like that. So this is the monotone fiber. And then if you push this off by parallel translation, this is giving you a monotone Lagrangian torus in CP2, depending on n. Right, so we'll call this, right, so we'll call the fiber, so it's Ln. Right? But this had us confused for a while, this thing. So looking at it, because that's a smooth right angled corner there, that's a smooth corner. This Lagrangian torus sits in the boundary of a cube, right? This is just a cube. So we'll see that L is contained in the boundary of a cube. But, okay, so now if I'm talking about choosing spheres in the complement, turns out you can always choose a sphere that's disjoint from this cube. So we can choose S disjoint. So S is a sphere in the complement of L. I can choose S disjoint from the cube. So then you take the image, right? So then you go LS. This is going to give me some Lagrangian torus in the ball, but now it's going to be a torus. It's still going to in the boundary of the cube, contained in a ball. Because, right, so S is somewhere here when you project it. So you move S up to infinity, the cube's still going to be there. Right. So it's okay. So it's a torus, it sits in the boundary of the cube. In the ball you can always include in R4 or C2. So now you have a torus in C2, which sits in the boundary of the cube, but there's no knotting of cubes in R4. You can just rescale them and somehow shrink to the origin and scale them back out. So this implies that the image here in C2 is the Clifford torus. Somehow so it's sort of so in the other direction, you can take the standard product Clifford torus in C2, move it around by a Hamiltonian isotopy, land in the ball, then include the ball in CP2, and then that torus in CP2 is in the same Hamiltonian isotopy class as these LNs. Right, okay, right, so we'll come back to these examples. Right, okay, right, so I was going to say, right, sorry, so the theorem is them, right, so the theorem's here. Right, so the famous one is independent proofs by Galkin, Mikhalkin, also by Viana. So I think even once this construction was known, there's also conjectures by Galkin and Uznich also about this. But anyway, so there's two independent proofs. Galkin and Mikhalkin, they're thinking more about algebraic degenerations. Viana works with these almost toric vibrations. So what they prove is that if, these tori L, A, B, C lie in different Hamiltonian isotopy classes. In CP2. So in other words, if you choose different Markov triples, you get different Lagrangian tori. Okay. So in particular, where there's infinitely many Markov triples, I get infinitely many distinct Hamiltonian isotopy classes of Lagrangian tori in CP2.
And are there more?
We don't know. But I guess that's a thing. I suppose people always ask that. Maybe they were asking that about the Clifford torus, then the Clifford and Chekhanov torus. So, yeah, I don't know how to get anymore. Right. So, right. So, what then we proved? Well, okay. Anyway, there's infinitely many, but each of those infinitely many, you get 3 Hamiltonian isotopy classes in the ball, and it turns out they're distinct as well. Except in the 2 cases we just talked about, right? So if as long as ABC is not, I want it to be, so 111 is the, that gives you the Clifford torus. 112 is the Chukhanov torus. So if we exclude these two cases, then the three tori, right, so it's L, A, B, C, S, I. Right, so there's three Hamiltonian isotopic classes of spheres in the complement. These correspond to tori in the ball, and they're also different. Right, so are represent distinct classes. Right, of tori. Hamiltonian isotopic classes of tori in the ball. So in a sense, there's 3 times as many in the ball as in CP2. Right. Okay, so now. So I was wondering, let me do this very quickly. So I was wanting to talk a little bit about quantitative estimates of these things. Right. Okay, right. Well, so maybe just very quick, right? So very brief, right? So the idea here. Right, it's good, right? So it's all, well, there's different ways of proving it. One way of proving these things is to study Maslov 2 disks, kind of counts of Maslov 2 disks. And, right, well, so one of them's our collaborator. So if we're going to follow, right, so following, right, so this is ideas of Galkin. We know a lot about the Maslov 2 disks with boundary on these Lagrangian tori. So, okay, so it's what to do with my picture. Lost it. Right. Well, okay, right. So remember, right, so we have this is going to be a moment polytope, maybe this is the Ln. So this is going to be a moment polytope for one of the weighted projective spaces. The thing is, I can see 3 families of Maslov 2 disks here. Right, so you just draw this, say we draw this horizontal line segment. That's a line segment. If I multiply it by a torus, by a circle in the same direction, that circle, so then I'm going to get a little cylinder here, but that circle is the vanishing cycle as you approach the boundary. So as you approach the boundary here, that circle's going to collapse. And then sitting above this, you would see a disk. And that's a Maslov 2 disk. There's another one here. And then there's another one here by drawing a line segment perpendicular to this boundary. So there's 3 Maslov 2 disks, 3 families of Maslov 2 disks I can see. So what this is, the boundaries of those disks, so the boundaries. So just the boundaries of the disks I can see, or the visible disks, right? So the boundaries of the 3 families of Maslov 2 disks. Maslov 2, we just think just means area 1, so check the areas 1. Right, so are the, so according to their paper, right, so these are called the extremal classes. Extremal classes, F. I'm taking the boundary, so they sit inside the first homology of the Lagrangian. Okay. Right, so you take one of these Lagrangians coming from a weighted projective space. I get the 3 extremal classes in the homology. And then we can just define delta star L. This is just the convex hull of the extremal classes. So if we take real homology, this would be a vector space, take the convex hull. Okay, so we can do that. You can also define delta L. So this is going to be the convex hull of another set of classes in H1 of L. But these are the classes where alpha is the boundary of beta, and beta is represented by a Maslov 2 disk. And then, right, and then the theorem is these two sets are the same. So this is kind of a great thing, right? So we don't know exactly what, at least I don't. I don't know exactly what all Maslov 2 disks are, but at least I know the convex hull of them. So in particular, if you want to prove this, if you want to prove that these tori are distinct, you just say, well, okay, on the one hand, the extremal disks determine the moment polytope, right? Because it's, well, I mean, it's just determined by classes which are perpendicular to the edges. So the extremal disks determine the moment polytope, but this delta L is a well-known symplectic invariant. So if you apply symplectomorphisms, Maslov 2 disks go to Maslov 2 disks, and counts of them are independent of J. So that already proves that. Okay. Right. Okay. So right. Okay. I'm going to skip. So our proof, okay, sort of goes on. We can also get our proof on the same line. So once we have this sort of information about Maslov 2 disks, we can really start. Right. We can still control in the ball what these. Well, right. So our idea is, okay, suppose this was false, then you'd get symplectomorphisms of CP2, which are preserving the Lagrangian torus, but messing around with homology classes in the complement. And somehow this gives you a lot of rigidity on what symplectomorphisms can look like, if there's no symmetries of the moment polytope. So that's okay. So that's very roughly the idea there. Okay, so I was trying to say something quantitative. 5 minutes here. But by the way, this same story, this is all CP2. You can play the same game for S2 times S2. And it's kind of, right, so S2 times S2, okay, it's the moment polytope there. Then you're kind of relating Hamiltonian isotopy classes in S2 times S2 to Hamiltonian isotopy classes in the cube. And it turns out you always get 4. Right? So you have to move like this line at infinity off. That has Chern class 2 ways to do that, 2 ways to do that. But now there's an extra quirk, because in S2 times S2, the symplectomorphism group and the Hamiltonian group are different. So then you get twice as many sometimes by flipping the 2 factors. So there's this extra complication. In S2 times S2, you can produce Lagrangian tori, which is symplectomorphic, but not. Anyway, right, so just 2 minutes left. I just want to quickly run through what I was going to say about quantitative. Right, so we'd like to understand the goal here. We'd like to understand these tori quantitatively. Right, so what do they kind of look like? Are they complicated? Right, and then there's a slightly sort of complicated or discouraging results due to Lee or Lingen or Viana. So if you take the Gromov width of CP2 and then you take off one of these tori, so the Gromov width of the complement, right, turns out this is always greater or equal to 1. So just by drawing the pictures, actually, so it's equal to 2 for the Clifford torus and the Chekhanov torus, but it's always equal to 1. So in a sense, the tori never get too big, right? So they're always small in the sense that there's always the big ball in the complement. But okay, right. But instead of looking at balls in the complements, you can also ask how small a ball can you embed the thing into. So we call this. So this is called the outer radius. So if we take L in CP2, we can define the outer radius of L. So this is going to be an inf of C such that what? Right, so there exists the phi symplectomorphisms of CP2, phi of L contained in the ball of size 3. The C, sorry, right? So B4C, we just, to fix things, this could be a fixed subset of the ball of size, so C less than 3 here, of the ball of, so just a round ball of capacity C inside the ball of capacity 3. So this is some kind of squeezing invariant, right? So it's how small a ball you can squeeze the things into. So in a sense, if L is big, then this capacity should be bigger. Okay, we can also, if the thing happens to be off of infinity already, then you can define the ball version, which is exactly the same definition, but I just want phi to be a compactly supported Hamiltonian diffeomorphism of the ball. So then, okay, so what we know about this? So theorem. Right. So first thing is that the outer radius of ABC is. Right, what is the outer radius of CP3? All right, it's one more sentence here. This thing. Right. Here we go. Right, 3, 1 minus 1 over b squared. So in other words, so if it turns out if any of these Markov numbers are going to infinity, it turns out the middle one, or the b, has to go to infinity, and then the outer radius is going to have to go towards 3 fairly fast. So in other words, as you move down the Markov tree, you somehow can't squeeze these tori. So in that sense, they're getting big. In fact, we can even be more precise. So if Ln, so this is the torus I wrote down, right? So this is the torus for the Markov triple Gn plus 1. I want to think of this as a torus in the ball. So if I'm thinking of it in the torus in the ball, I want to say that this is sitting inside the ball, in bounding a cube, right? So in the boundary of the cube. So then, so rho Ln, we won't have an S here, right? So it's so rho Ln is right 3 minus. Let's forget this thing. All right, so 3 minus 1 over Gn plus 1 plus 2 Gn. But rho of Ln, we know exactly. All right, so rho of Ln is 3 minus 1 over Gn plus 1. So again, as n goes to infinity, this is converging to 3. So conclusion of that is, if you take the outer radius of Ln, for sure that's less than or equal to the outer ball radius of Ln, just because this is an infimum over a smaller set. This I have a formula for, and then you can prove that that's strictly less than the outer radius of Ln plus 1. Just by comparing these two numbers. So this number is strictly less than this. So in other words, this outer radius can distinguish all of those, at least this one family of Markov tori. So I haven't got time to prove it, but so this sort of says, in a sense, these things, we can sort of distinguish them quantitatively. So the radius goes up.
So the second line is supposed to be for the ball, or so you have rho Ln, and the second line is also rho Ln. Rho Ln.
Yeah. Oh, sorry. Right. Yeah.
Rho B or rho.
Oh, sorry. Right. Yeah. Sorry. Yeah. Exactly. Right. Yeah. It should be rho B. Exactly. Right. Yeah.
And then, oh.
Yeah. So rho B. I know exactly rho L. I just have the lower bound. But that's what I need to. So that's how I get this inequality. So I just have a lower bound on this, which is enough to prove that. Right.
So that theorem is also rho B. Last theorem, the quantities for rho B, right?
Oh, sorry. This should be greater or equal. Sorry. Sorry. Yeah, greater. Yeah, we don't know exactly what they are. This is just a lower bound on that. Yeah, but somehow, yeah, I don't know. They're kind of surprising you get to even so precise on these things. Okay, right, but these things are sort of possible to prove because we know so much about holomorphic disks, and they obstruct these things. All right. Yeah, I'll leave it there.